You think comets are predictable. Ice and rock, sun gets closer, tail appears, story over. But on July 1st, 2025, a 20-inch telescope in Chile's Rio Hurtado Valley caught something that breaks every rule we thought we knew. An interstellar visitor moving at 137,000 miles per hour. Not from here. Not like anything we've seen. And by late August, when its tail exploded into view, spanning 56,000 kilometers, astronomers realized they weren't just watching a comet. They were witnessing something that could rewrite our understanding of how worlds form around distant stars. 3I Atlas, the third confirmed interstellar object to enter our solar system, the first to grow a tail we could actually study, and the first to reveal chemistry so bizarre, so impossible by our standards, that NASA's most powerful telescopes are racing to decode what it means before it disappears forever. What makes this visitor so strange? Its tail didn't just grow, it erupted. And the chemistry powering that eruption contains secrets that could tell us whether our solar system is common or impossibly rare in the universe. If you value documented space science like this, subscribe. It's the best way to support our work. Also, comment from which city you're hearing this from. This script is researched and factual, using sources from Martin Cordner's peer-reviewed study published in RSEV on August 25th, 2025, through NASA Goddard, Space Flight Center's James Webb Space Telescope observations, and real-time data from the Gemini South Telescope's multi-object spectrograph documented on August 27th, 2025. Now back to the information. 3I Atlas was 670 million kilometers from the Sun when Atlas Survey Telescope first caught it. That's Jupiter distance. Most comets stay dark and quiet that far out. They need to get much closer before solar radiation starts melting their surface ices. But this object was already glowing, already active, already breaking the rules. David Jewett led the Hubble observations from UCLA. When his team pointed the space telescope at 3I Atlas on July 21st, the comet was 277 million miles from Earth. What they found was a teardrop-shaped cocoon of dust streaming from the nucleus. Not water vapor, like normal comets, something else entirely. The hyperbolic trajectory told the story. This wasn't bound to our sun. It came from somewhere else, traveled for possibly 7 billion years through interstellar space, and now it was passing through our neighborhood at speeds that made tracking difficult. Like glimpsing a rifle bullet for 1,000th of a second, Jewett said. But the real shock came from what was inside. NASA's James Webb Space Telescope locked onto 3I Atlas on August 6th, 2025. Distance from the Sun, 3.32 astronomical units. Still way out in the cold. The near-infrared spectrograph started picking apart the light coming from the comet's coma, the cloud of gas and dust surrounding its nucleus, and what it found made no sense. Carbon dioxide. Massive amounts of carbon dioxide. An 8-to-1 ratio compared to water, the highest ever recorded in any comet, 6 standard deviations above normal values. This wasn't just unusual. This was impossible by solar system standards. Martin Cordner from NASA Goddard led the study. His team had been waiting for an interstellar visitor like this, telescopes already reserved, plans already made. When 3I Atlas appeared, they had one shot to get it right. What they discovered changed everything. Normal comets in our solar system have maybe a 1-to-10 ratio of carbon dioxide to water. Some have less. 3I Atlas had 8 times more carbon dioxide than water. That meant its formation environment was completely different from anything in our solar system. Either it formed in a region rich in carbon dioxide ice, or something had happened during its billion-year journey through space that cooked its surface into something new. The carbon isotope ratios told another story. Carbon-12 to carbon-13 signatures similar to Earth. The building blocks were familiar, but the proportions were alien, like finding a house built with the same bricks as every other house, but assembled in a way that defies physics. Stephanie Milam, astrochemist at Goddard, had a theory. 7 billion years traveling through the near absolute zero of interstellar space, constant bombardment by cosmic rays, star-forming regions where supernovae exploded, radiation fields that could cook a comet's surface into something unrecognizable, a shell of carbon dioxide ice created by processes that don't exist in our quiet corner of the galaxy. But the tale was just getting started. By mid-August, 3I Atlas was showing the first signs of what was coming. Test telescope data revealed the comet had been active since at least May rollers, 2 full months before its official discovery. Already outgassing at 6 astronomical units from the Sun, already violating the rules about when comets wake up. The Hubble images from July showed a faint and broad tail pointing away from the Sun, standard comet behavior. Small dust particles blown away by solar radiation pressure. but the tail was foreshortened, pointing almost directly away from Earth, mostly hidden behind the coma. The real show was still to come. August 27th changed everything. Gemini South Telescope in Chile, 8.2 meters, onda of collecting power focused on 3I Atlas through its multi-object spectrograph. What they captured was a comet in the process of transformation. The antisolar tail had exploded into visibility, 30 arcseconds in angular length. 56,000 kilometers of dust and ice streaming away from the nucleus. Karen Meach from the University of Hawaii led the observation program. Students from Hawaii and Chile joined remotely, watching in real time as the tail grew before their eyes. The coma had expanded to a radius of 23 kilometers. Production rates were off the charts. This wasn't gradual awakening. This was eruption. The sun-facing plume told a different story. Enhanced outgassing from the heated, sunlit surface where carbon dioxide ice was sublimating faster than water ice. The nucleus itself, measured by Hubble, was somewhere between 440 meters and 5.6 kilometers across. Small for something causing such a massive display. But size wasn't the issue. Chemistry was. The spectral data from Gemini revealed dust broadly similar to solar system comets, similar processes, similar materials. But the proportions were wrong. The carbon dioxide dominated everything else. Water was there, but secondary. Carbon monoxide at normal levels. Carbonyl sulfide present but not dominant. It was like looking at a familiar recipe prepared with completely different ingredient ratios. Recognizable but fundamentally alien. The questions multiplied with every observation. How does a comet maintain such high carbon dioxide content through 7 billion years of interstellar travel? What kind of formation environment produces 8:1 carbon dioxide to water ratios? And why was 3I Atlas active so early and so violently compared to normal comets? Sphere-X telescope added more data between August 7th and 15th. Multispectral observations at distances between 3.3 and 3.1 astronomical units from the Sun clearly resolved coma, rich in carbon dioxide and water, no visible jets or outbursts, just steady, massive production of gas and dust. The tail continued growing, very large. Telescope images from August 23rd showed classic cometary structure developing, the sun-facing plume visible in all images, the anti-solar tail pointing left, away from the sun, growing longer with each observation. By late August, the transformation was complete, and what had started as a faint smudge in July had become a textbook comet with one crucial difference. Its chemistry was unlike anything ever recorded. Bryce Bolin from Eureka Scientific watched the August 27th observations. Every interstellar comet is a messenger from another star system, he said. By studying their light and color, we can begin to understand the diversity of worlds beyond our own. 3. I Atlas was carrying a message, not just about its own formation, but about the conditions that exist around other stars, about whether planetary systems like ours are common or rare, about the processes that create the building blocks of life. The carbon dioxide dominance pointed to formation scenarios that don't exist in our solar system. Maybe 3I Atlas formed close to the carbon dioxide ice line in its parent protoplanetary disk, where carbon dioxide freezes but water remains gaseous. Maybe it experienced radiation levels that our solar system never saw, cooking its surface ices into new configurations, or maybe it spent so long traveling through interstellar space that the very medium between stars changed its composition. Interstellar clouds, star-forming regions, supernova remnants. 7 billion years of exposure to environments our comets never experience. The October timeline loomed. 3I Atlas would reach perihelion on October 30th, its closest approach to the Sun at 1.4 astronomical units, just inside the orbit of Mars. Close enough for Mars orbiters to possibly observe it. Close enough for massive outgassing and potentially dramatic fragmentation. Comet 2. I Borisov, the previous interstellar visitor, had fragmented on its way out of our solar system. 3I Atlas might suffer the same fate. Or it might survive to give us more data as it emerged from behind the Sun in November. The November observations were already planned. Gemini North Telescope in Hawaii standing by, Bryce Bolin ready to host another public viewing session. The chance to see what remained of 3I Atlas after its close encounter with our Sun. But the August tail growth had already told us the most important story. This wasn't just a comet, this was a time capsule from an alien world. A messenger carrying chemical signatures from stellar environments we can barely imagine. The 8:1 carbon dioxide to water ratio, the early activation at 6 astronomical units, the explosive tail growth that defied normal comet behavior. Every measurement pointed to the same conclusion. Our solar system might be far more unusual than we thought. 3I Atlas formed around a different star, in conditions unlike anything in our planetary system. It traveled for billions of years through environments that changed its very composition, and when it finally entered our solar system, its tail became a banner advertising the diversity of worlds that exist beyond our experience. The chemistry doesn't lie. Carbon dioxide doesn't dominate comet comas unless something fundamental is different about their formation or evolution. Water doesn't take second place unless the environment where that comet formed was alien to our experience. Jacqueline McCleary from Northeastern University summed it up perfectly. Is our solar system common or rare? It seems to be relatively rare, and this helps us quantify that 3I Atlas was more than a comet growing a tail. It was proof that the universe contains worlds formed under conditions we're only beginning to understand. The tail that erupted in late August was advertising chemistry from an alien stellar system, carried across billions of years and trillions of miles to deliver a message about the true diversity of planetary formation. The message was clear. We are not typical. Our solar system, with its familiar water-dominated chemistry and predictable comet behavior, might be an exception rather than the rule. 3I Atlas came from somewhere else, somewhere with different rules, different chemistry, different possibilities, and its tail, growing rapidly through late August as it approached our sun, was the first clear signal we've ever received from that alien world. On September 5th, 2025, ground-based telescopes captured images of 3I Atlas showing the full development of its anti-solar tail. The nucleus remained intact. The outgassing continued. The chemistry stayed impossible by our standards. But in November, when 3I Atlas emerges from behind the sun on its outbound journey, we'll get one more chance to study this messenger from an alien world, to understand what its chemistry tells us about the conditions around other stars, to learn whether worlds like Earth are common or impossibly rare. The implications hit harder when you look at the numbers. TESS telescope revealed 3I Atlas was producing gas and dust at rates that shouldn't be possible. Normal comets at 6 astronomical units from the sun are dormant. Ice stays frozen. Activity waits until they get closer, usually inside 5 astronomical units. 3I Atlas was already blowing material into space in May 2025, 2 months before discovery. 6.0 astronomical units from the sun. Something was driving activity levels that violate everything we know about comet physics in our solar system. The production rate measurements told the story. 23-kilometer coma radius by August, steady outgassing without the bursts and lulls typical of normal comets. No detected outbursts despite the massive activity. Just continuous, impossible chemistry, creating a display visible across millions of kilometers. Ground-based telescopes worldwide joined the effort. Las Cumbres Observatory captured time-lapse sequences showing 3I Atlas moving against background stars. The velocity was obvious, even in still images, 137,000 miles per hour when discovered, accelerating as it approached the sun. Canada-France-Hawaii telescope on Mauna Kea confirmed the marginal coma with potential tail-like elongation on July 2nd, 3 arcseconds in angular length. First proof. This wasn't an asteroid, but an active comet. First hint of what was coming. Lowell Discovery Telescope in Arizona provided independent confirmation the same day. Deep Random Survey in Chile added supporting observations. By the time the Minor Planet Center announced the discovery, they had collected 122 observations from 31 different observatories. The orbital mechanics painted a clear picture. Hyperbolic trajectory. Eccentricity greater than 1, coming from the direction of Sagittarius constellation, where the galactic center lies hidden behind dust and stars, traveling too fast to be captured by our sun's gravity, a one-time visitor that would never return, but the chemistry was writing a different story, one that required digging deeper into what makes 3I Atlas fundamentally different from everything we've seen before. Water ice was there, spectroscopic signatures clear and unmistakable, but buried, overwhelmed by carbon dioxide in proportions that challenge basic assumptions about comet formation. The water to carbon dioxide ratio suggested an environment where water was scarce or systematically removed during formation. Carbon monoxide levels stayed normal. 1.4 to 1 ratio with water. Expected values that matched solar system comets. This wasn't a case of wholesale chemical weirdness. This was selective enhancement of carbon dioxide that pointed to specific formation conditions. Carbonyl sulfide added another piece to the puzzle. Present but not dominant. Sulfur chemistry proceeding normally while carbon dioxide dominated, like finding one instrument playing too loud in an otherwise normal orchestra. The dust grain analysis revealed more surprises, particle sizes consistent with normal comets, reflective properties within expected ranges. Whatever made 3I Atlas chemically unusual hadn't affected the basic physics of how dust particles formed and were ejected from the surface. This suggested the anomaly was in the ice composition, not the overall structure. 3I Atlas had a normal comet framework filled with alien chemistry, a familiar body type carrying unfamiliar contents. Nordic optical telescope observations by David Jewett and Jane Liu on July 2nd confirmed the object was clearly active with a diffuse coma. The activity was real, measurable, and growing stronger as the comet approached the sun. But the chemical signature powering that activity was unprecedented. The trail of observations built a timeline. May, already active at 6 astronomical units. July 1st, official discovery. July 2nd, confirmed as active comet. July 21st, Hubble captures detailed images. August 6th, James Webb reveals impossible chemistry. August 27th, Gemini South documents explosive tail growth. Each observation added pieces to a puzzle that challenged fundamental assumptions about how comets form and evolve. 3I Atlas wasn't just different, it was systematically impossible by solar system standards. The age estimates made everything more puzzling. Kinematic analysis suggested possible ages exceeding 7 billion years. Older than our solar system, a relic from an era when the galaxy was younger. Stars were forming under different conditions. Planetary systems were assembling according to different rules. Matthew Hopkins from Oxford told BBC News the kinematics suggested the object could have originated from the Milky Way's thick disk, an ancient population of stars with different chemical compositions, different planets, different comets. If 3I Atlas was 7 billion years old, it had witnessed galactic evolution. We can only theorize about star formation rates that dwarf current levels, supernova frequencies that would bathe interstellar space in radiation, chemical evolution that produced carbon dioxide, rich environments our models barely consider. The radiation cooking theory gained support from multiple angles. Stephanie Milam's calculations showed how cosmic ray bombardment over billions of years could alter surface chemistry, high-energy particles breaking down water molecules while leaving carbon dioxide intact. Selective chemistry driven by interstellar radiation fields, but the timeline created problems. 7 billion years of cosmic ray exposure should have eroded the nucleus completely. Something protected. 3I Atlas during its journey. Something kept its chemical signature intact across distances and timescales that should have destroyed any comet. The insulation hypothesis emerged. Water ice buried beneath layers of more stable materials. Carbon dioxide created or concentrated at the surface by radiation processing. A cooked shell protecting pristine materials underneath. The surface chemistry telling one story while the interior held different secrets. This could explain the delayed water release. Carbon dioxide sublimates easily at low temperatures. Water ice needs more heat. If 3I Atlas had a carbon dioxide-rich shell over water-rich interior, the observed chemistry made sense. The shell was talking first. The interior would speak later. The October perihelion promised answers. At 1.4 astronomical units from the Sun, close enough to heat deeper layers. Close enough to potentially strip away the processed shell and reveal what lay beneath. Close enough to test every theory about 3I Atlas's true composition. Mars orbiters prepared for the encounter. NASA's Mars Atmosphere and Volatile Evolution Orbiter positioned to observe 3I Atlas as it passed within 30 million kilometers of the red planet. The comet would appear large and bright in Mars' sky, potentially revealing coma details impossible to see from Earth. Perseverance rover. Mars Reconnaissance Orbiter. Curiosity rover all tasked with observations if the geometry worked out. A chance to study an interstellar visitor from multiple perspectives simultaneously. Ground truth data on coma chemistry and structure. European Space Agency's Mars orbiters joined the effort. Mars Express, Trace Gas Orbiter, ExoMars program assets all capable of contributing data. The most comprehensive study of any interstellar object ever attempted. But the August tail growth had already provided the crucial evidence. The rapid development from barely visible elongation to 56,000 kilometer display showed 3I Atlas, responding to solar heating in ways that confirmed its alien chemistry. Normal comets build tails gradually. Ice sublimates slowly as solar heating penetrates deeper into the nucleus. Activity increases smoothly as distance to the sun decreases. Predictable physics producing predictable results. 3I Atlas exploded into visibility. Tail growth that jumped from 3 arcseconds to 30 arcseconds in 6 weeks. Production rates that overwhelmed normal scaling relationships. Chemistry driving activity levels that shouldn't be possible at those distances from the sun. The sun, facing plume visible in very large telescope images from July through August, showed another anomaly. Enhanced outgassing from the sunward side, yes, but maintaining that enhancement over weeks of observation. Normal comets show variable activity as they rotate and different surface areas face the sun. 3. I-Atlas maintained steady, enhanced sunward outgassing throughout the observation period. Either it wasn't rotating normally, or its entire sunward hemisphere had uniform composition, unlike any normal comet. Another small impossibility in a growing list. The inner coma analysis from August 26th, images revealed fan-shaped structure within 5 arcseconds of the nucleus, slightly brighter on the sun-facing side. Systematic outgassing patterns that suggested large-scale composition differences across the nuclear surface. This wasn't random chemistry, this was organized, structured, systematic difference that pointed to formation processes unlike anything in our experience. 3. I-Atlas had been assembled according to different rules in an environment with different chemical priorities. The comparison with other interstellar visitors became crucial. 1, Oumuamua in 2017 showed no clear coma, no obvious comet activity, classified as an asteroid but with acceleration patterns that suggested outgassing below detection limits, too faint for chemical analysis. 2, I. Borisov in 2019 provided the first comparison point. Clear comet activity, detectable coma, chemical analysis possible. But 2, I. Borisov had higher carbon monoxide to water ratios compared to 3, I-Atlas. Different chemistry, different formation environment, different story. 3 interstellar visitors, 3 completely different chemical signatures. No pattern except diversity. No standard interstellar comet chemistry, each visitor carrying unique chemical fingerprints from alien stellar environments. This suggested the galaxy contains a vast diversity of planetary formation conditions. Different stars producing different chemical environments. Different protoplanetary disks assembling planets and comets according to local conditions that vary dramatically across interstellar space. 3 I-Atlas represented one sample from that diversity, a messenger from a stellar environment where carbon dioxide dominated comet formation, where water was scarce or systematically removed, where radiation fields or chemical processes created ice compositions impossible in our solar system. The November observations would test survival theories. Would 3 I-Atlas emerge intact from perihelion? Would the close solar encounter strip away the processed shell and reveal interior chemistry? Would fragmentation create multiple pieces carrying different chemical signatures? Gemini North Telescope in Hawaii stood ready. Bryce Bolin prepared for follow-up observations with public participation. The same educational approach that had documented the August tail explosion would track 3 I-Atlas through its post-perihelion emergence. But the late August tail growth had already delivered the most important message. This wasn't just unusual chemistry. This was proof of concept that alien planetary systems operate according to different rules than our own. The 8-to-1 carbon dioxide to water ratio wasn't just an anomaly. It was evidence of systematic differences in how worlds form around other stars. The rapid tail development wasn't just surprising behavior. It was demonstration of chemistry driven by processes our solar system never experienced. 3. I-Atlas had traveled 7 billion years to deliver a message about the true diversity of planetary formation. Its tail, exploding into visibility through late August 2025, was the signature of an alien world finally close enough to our sun to reveal its secrets. The chemistry doesn't lie, the tail growth patterns don't lie, the systematic differences from normal comet behavior don't lie. We are not typical. Our solar system, with its familiar water-dominated chemistry, might be a rare exception in a galaxy full of worlds formed under radically different conditions. 3 I-Atlas proved it. One visitor from interstellar space carrying chemistry that challenges every assumption about normal planetary formation, one tail growing rapidly through late August, advertising the reality of alien worlds we're only beginning to understand. In 2030, the Vera Rubin Observatory will begin operations, designed to detect dozens of interstellar objects, each carrying chemical messages from different stellar environments, each testing our understanding of how diverse planetary formation can be. 3. I-Atlas was the preview, the first clear chemical signature from an alien world, the proof that our solar system's chemistry might be far more unusual than we ever imagined. The tail that erupted in late August was just the beginning.